Hello everyone! In this lecture, we will study a vulnerability called SQL injection. But before that, let's have a quick recap on what is SQL. SQL is a query language used in the context of relational databases. The idea here is that we can store data in a database that may consist of several tables. Each table can have one or more columns that store data of a specific data type. And these tables can store millions of rows, records, or entries, however we choose call them. So, in the context of relational databases, SQL, or structured query language, is a standard language used to read and write data in such databases. SQL is a simple yet powerful language for processing data in databases. But before we dive into that, let's take a brief look at the most popular database engines we are likely to encounter. MySQL is the most popular database you will encounter in the context of web applications. The reason for this is that it is free, fast, and a perfect fit for small to medium-sized projects. And this is also why our focus will be on MySQL in this lecture. Note that there is also a forked version of MySQL called MariaDB, which is becoming increasingly popular among Linux distributions. But since it is a drop-in replacement for MySQL, there is really no difference between the two, and therefore people continue to use the term MySQL when referring to MariaDB. Then Microsoft SQL Server is also a popular database server commonly used alongside other Microsoft products. So if there is a web application written in Microsoft's ASP.NET, it is very likely that it will use Microsoft SQL Server as its database backend. Then we have PostgreSQL, which is also a free software like MySQL, but it is less popular than MySQL because it is somewhat slower for basic functionality. However, a standout feature of PostgreSQL is its better transaction support and customization options. For example, PostgreSQL allows the creation of custom database functions in various programming languages. Next, we have the database giant Oracle with its highly expensive database product featuring many advanced features, integrated analytics, and whatnot. Oracle databases are typically used in large enterprises or government institutions, but they are usually not directly accessible over the web. And the last database engine to mention is SQLite. SQLite is actually not a database server, but a library that can be used to store data in files and process it using SQL. It is extremely popular as many software products, including web browsers, use SQLite databases for their internal storage. The reason for this is that SQL is a powerful and convenient language for data manipulation. Anyhow, even though in the rest of this lecture we will use MySQL as an example, please note that all SQL database engines are similarly affected by SQL injection. The exploitation techniques are the same, with only small nuances due to SQL syntax differences across different SQL engines, but these differences are generally insignificant in practice. Therefore, most of what we discuss in this lecture can be applied almost one-to-one to any SQL database engine out there. Okay? Okay, now let's take a look at the SQL language. Let's say we want to have a database table with columns for ID, name, last name, age, and a status indicating whether the person is alive. We can use the createTable statement to create such a table, specifying here the column names and their data types. Then we can use insert statements to populate the table with data. Note that when specifying numeric values, we don't have to use quotes around them, though we can if we wish. Also note that in MySQL, true is equivalent to 1 and false to 0, as we can see here. Then the most popular statement is the select statement because it allows us to retrieve data from a table based on conditions that we specify here in the where clause. So this should return the age column from persons where name equals John and last name equals Smith. And we get back a single record with a single column containing the value 83. Note that for quoting, we can use either single quotes or double quotes, but it is much more common to use single quotes in SQL. The conditions in a where clause can be much more advanced. We can use multiple and or conditions and even subqueries, as you can see here. And that is the power of SQL. There are also quite a few built-in functions that we can use in a query. Then we can use the order by clause to sort the returned records by specific columns and the limit clause to restrict the number of records returned. And here is the result we will get when executing this query. We can use the update statement to set values for specific columns where this condition is satisfied, and the delete statement to remove records that match a specific condition. So that is SQL in a nutshell. As you can see, it is a very powerful and human-readable language for manipulating datasets. Now, what is SQL injection? Let's take a look at a basic example. Let's say we have a website that shows information about products. The information is stored in a database, and we query the database based on the product ID received here in the URL parameter. So this would be our PHP code that queries the database based on the received product ID. Select all columns from the products table where the column ID is equal to the ID received in the get parameter. This will return a result which we can process and display to the user. Very good. So indeed, this code will work as expected, but only as long as the value we receive here is a numeric ID of a product. Now, what would happen if an attacker submits this type of value in the ID parameter? After we insert this value into our SQL query here, this will be the resulting SQL query sent to the database. What happened here is that the attacker used single quotes here to terminate the value of the ID column and extended our SQL statement with an OR condition that looks for records where the column hidden contains the value 1. Effectively, the attacker modified our SQL statement by injecting SQL code into our query. So that's an SQL injection attack. The attack became possible because we included untrusted user input into the SQL query without validating it. The simplest measure here would have been to check that the received value is an integer. However, for string values, we would need to use escaping. Here's an example of how we could have prevented this attack by escaping the received value. We will discuss it in more detail, but essentially it means prepending a backslash before quotes, thereby indicating that these quotes are not value terminators, but are part of the string value. In practice, the most common SQL injection location is in the where clause of the select statement, as we saw here in this example. Other common SQL injection locations are the where clause in the delete statement, the values clause in the insert statement, and for the update statement, there are two locations, the where clause and the set clause where we pass the new value of the column. In principle, SQL injection can occur anywhere. For instance, even in table and column names if we build our queries by including untrusted user input there. From an exploitation point of view, it usually does not matter much where exactly the untrusted input is included. However, what does matter a lot is the type of query the injection occurs in, as that determines how much an attacker can achieve by exploiting the vulnerability. And here we come to the question of the impact of an SQL injection attack. What is the impact of it? What is the worst thing an attacker can achieve with it? In this particular example, the attacker can fetch some hidden products from the database table, which perhaps does not seem like a too terrible security issue. However, this was just a basic example. In general, as a rule, SQL injection enables unauthorized database reading. And by this, we do not mean some limited reading of some columns from a specific table used in the affected SQL query. No. Unauthorized database reading means reading any data from any database and table that the database user has access to. As you will see, there are techniques that allow us to read data from any database table, regardless of the type of SQL statement or location of the injection within the statement. So, as a rule, SQL injection results in the loss of data confidentiality. Then unauthorized deletion and modification can also sometimes be achieved, but only sometimes, as this depends on the type of SQL statement in which the injection occurs. For instance, it is not possible to execute delete or update statements inside a select query. And if we have SQL injection here in a delete statement, we will only be able to delete arbitrary records from the table specified here. There may be some exceptions to this rule, but these are relatively rare, as you will see. And then SQL injection can also be used for subversion of application logic, meaning that if the application performs some specific actions based on the returned database result, then we can use an SQL injection attack to influence the returned result and thereby force the application to perform actions that we otherwise could not perform. A classic example here is using SQL injection in a login form to bypass authentication. Here we assume that authentication is implemented by executing such an SQL query where the submitted username and password are directly included in the query. The resulting SQL statement would look like this and would allow us to log in as the admin without knowing the admin password, because this condition will always evaluate to true. The actual password conversion will fail, but this injected part will always be true because 1 is equal to 1, making the entire condition evaluate to true. Of course, this is a somewhat naive example as it assumes that passwords are stored in plain text in the database, which shouldn't be the case. But anyway, let's move on to discuss various techniques for exploiting SQL injection. Let's take the same example that we see here, and let's try to figure out how we can exploit this SQL injection flow to read any database and table that the database user has access to. First, we assume that this attack is not blind, meaning that when we open this page, we can see the values of at least some of the columns that are returned as a result of this SQL query. In practice, these values would be shown in place of the product's name, description, and so on. So here the question is, how can we modify this query so that it returns columns from some other database table? Of course, if we could modify this part here, then it would be trivial. But here we can modify only this part, the ending of the SQL query. And this is where the SQL union operator comes to the rescue. The union operator combines the results of two or more select statements. Here is an example. Let's say we have two tables, teachers and students, and we want to select the age column from both tables. In order to do this, we perform select age from teachers union all select age from students, and we get the age values from both tables. Now, the keyword all here specifies that we want to include also the duplicate values in the result. Otherwise, the duplicates would be omitted. Anyway, using union in our injected payload, we can pull data from other tables into the result. So this enables us reading data from other database tables. Now, the requirement here is that the number of selected columns in both select statements and their data types must match. This means that if the leftmost select statement selects 3 columns, our union select statement must also select data from 3 columns. Otherwise, the SQL server would not be able to combine the results. In practice, the data types of the selected columns must not be exactly the same, but they must be similar. So there is some flexibility. But what should we do if we do not know how many columns the original select statement queries? Here is a simple technique for enumerating the number of columns being selected here. The thing is that in SQL, we are allowed to select columns that are not actual columns from some database table, but are constant values that will be returned as column values. This way, we can iteratively perform queries, increasing the number of selected columns with each query until our query executes successfully, which would mean that we have guessed the correct number of columns that are being selected here. In some cases, we would also need to guess the correct data type. To do that, we can replace these constants with a constant of the corresponding data type that we want to test. Once we have determined the number of columns and their data types, we can try to use union select to retrieve data from other database tables. Here's an example exploit payload that we might try to use. And this is how the resulting query sent to the database server would look. There are a couple of things to point out. In this case, our union select selects 4 columns. This will work assuming that this original select statement here also selects 4 columns. Here we are selecting 2 constants, followed by the username and password columns from the users table. Note that here we are using the limit and offset clauses to specify which record we want to be returned in the result. This is needed because the vulnerable website only uses the first record returned by the query. So by changing the offset, we can iterate over each record returned by the select statement. Next, note these 2 dash characters followed by a space character. MySQL recognizes this as the beginning of a comment and ignores everything that follows it. This allows us to discard the remaining part of the original SQL query after our injected payload. In essence, using an SQL comment lets us write our own ending of the original SQL query. Otherwise, we would have to carefully rewrite our payload to ensure that this quote character from the original query does not cause a syntax error in the final SQL statement. Alright, so this is how we can read arbitrary data from any database table that the database user has access to. However, in order to do that, we first need to somehow find out the names of tables and columns that exist in the database. So the question here is how to discover the names of tables and columns that are in the database. Database structure enumeration is relatively straightforward in MySQL, as this information is stored in a special database that we can access. For example, to get a list of databases that are available to the current database user, we can select column schema name from the information schema database and the schemata table. So this shows that we have access to 2 databases, information schema and e-commerce. To retrieve a list of tables in the e-commerce database, we can query table name from information schema tables, where table schema equals e-commerce, and we get the names of the tables in that database. To get a list of tables and their columns, we can select table name and column name from the columns table, where schema equals e-commerce. This table actually contains much more information about each column, such as its data type, which we can query if needed. Other useful values that we can query include the current database user, the name of the current database, and the version of the database server. In summary, this is how we can enumerate the database structure via an SQL injection attack. Blind SQL injection occurs when we are not able to observe the direct results of our SQL injection. Here is an example of such a blind SQL injection. So here is a PHP code that executes a delete statement where we can inject some SQL code here in the where clause. This injection is considered blind because this query returns no result and does not even report an error if the execution of the query fails. Typically, blind SQL injection occurs in delete, update, and insert queries, as these types of queries do not return any data. But it can also occur in a select query if the result of the query is not displayed on the returned web page. At first glance, a blind SQL injection might seem like a dead end, because how the heck can we extract any data if we don't get any output from the query? However, it turns out that there is a fascinating technique that allows us to extract data even in this type of blind SQL injection. And the technique here involves extracting information via timing side channels and SQL conditions. With timing side channels, we aim to influence the execution time of the query. In other words, we intentionally slow down the query to create a noticeable time difference, which we can measure and use to infer information. So for this purpose, we can use the MySQL benchmark function. Here we can specify the action to perform, and here the number of times it should be repeated. In this example, we are performing a hash calculation 1,000,000 times, which will take several seconds on a modern computer, thereby making the query noticeably slower. However, since this calculation is very CPU intensive, it may lead to a denial of service condition on the database server. Therefore, it is better to use the MySQL sleep function, where we can specify the delay in seconds for which the query execution should pause. This function also accepts floating point numbers, so we can also pause for less than a second if needed. Then we can combine this with SQL conditions to introduce a delay only when a specific condition is true. For example, we can use the MySQL if function. Here we specify the condition to check, here what should be executed and returned if the condition is true, and here what if the condition is false. In this example, we are checking whether the name of the current database is e-commerce, and if it is, the function will sleep for 1 second. Otherwise, it returns false immediately. So by measuring how long the query takes to execute, we can infer whether the database name is e-commerce or not. We can also use the exist statement together with a select subquery. If this subquery returns any result, then this condition will evaluate to true, and this subsequent condition will also be tested, which will introduce a 1 second delay. The point is that this condition will be tested and executed only if this condition is true. This way, the delay will be introduced only if this select subquery returned any result. Here's an example of a blind SQL injection where we check whether the first character of the password is the letter A. If it is, then the query will pause for 1 second. By using this technique, we can brute force each character of the password until we recover the entire value. As you can see, exploiting a blind SQL injection involves sending many requests and requires a lot of patience, but it is doable as long as we don't have to dump megabytes of data using this technique. There are 2 things to note about exploiting using a delete query. First, we must ensure that the conditions in the where clause return false. Otherwise, we risk deleting records from the table. The sleep function always returns false, so it does not pose a problem here in this example. Second, if the condition is successful, this sleep function will be executed for every record that matches this condition. So ensure that this condition matches only a single record in the database. Alright, that's it about blind SQL injection. A quick note about batched or stacked queries. By using batch queries, we might be able to execute more than one query in a single transaction. Here's an example of the infamous SQL injection attack that uses batched queries. Here, the attack targets automated license plate scanners that use optical character recognition to read vehicle license plate numbers. The hope is that the scanned license plate number is later used in an SQL query in an insecure way. The idea is that this part ends the original query, and here comes an additional query that attempts to drop the database. Using batch queries in an SQL injection attack is a very powerful technique, as it enables the execution of arbitrary SQL queries with the access rights of the database user. In the inline SQL injection attacks we have discussed so far, we cannot actually run arbitrary SQL queries. We can only modify the end of an existing query. And this is very limiting, as there is no way to execute operations like dropping or creating database tables. As you can see, the use of batch queries allows for the execution of any query as if we had direct access to the database server. However, the problem with this SQL injection technique is that its support depends on the database query method used by the vulnerable application. For instance, if we try to execute such a batched query using the PHP's MySQL query method, we will get a PHP fatal error. You have an error in your SQL syntax near drop table test. To succeed in executing such queries, the vulnerable code must use the MySQLi multi-query method, which supports batched queries. However, it is unlikely that this method would be used in the vulnerable code to send SQL queries. To summarize, whether this injection technique will work heavily depends on how the vulnerable application queries the database. So in most cases, this technique will likely not work. Let's talk about how to prevent SQL injection flaws, and this is where string escaping can be used. The idea here is to escape SQL special characters so that they are not interpreted as SQL string terminators. Here is an example. We can use the MySQLi real escape string function on a value to escape it and make it safe to be included in an SQL query as a string value. What it does is that if the value contains quotes, the function escapes them by prepending a backslash, and these quotes will then be interpreted as string literals that are part of the value, and thereby this prevents SQL injection attacks. What this function does is that it replaces these characters with these two characters. Strictly speaking, only backslashes and quotes need to be escaped. But escaping these characters can also be useful because this way, if you log our SQL queries, they are easier to read. For instance, here is how an escaped SQL query would look in a log file. While without escaping, new lines would break our logging system by causing one query to potentially span multiple lines. For an SQL server, escaping new lines does not matter because by the server, both the original and escape byte sequences are interpreted as a new line character. And by the way, in principle, we could use the PHP add slashes function instead to achieve a similar escaped result. This, however, is not recommended as using this function is not safe when used with certain non-UTF-8 character encodings. There is one Chinese character encoding that add slashes cannot correctly escape. If the database is using UTF-8 encoding, then this would not be a problem, but it is still better to use the real escape string function as it is aware about the database encoding and can safely escape strings even for those non-standard character encodings. Okay? Okay, very good. So we can use escaping to prevent SQL injection. However, at this point, it is important to stress that the escape parameter must be quoted, as otherwise escaping will not help us. Here's an example. Here we have the same code, but here we are not using quotes around the value as we were using here. The result is that now our code is vulnerable to SQL injection, as an attacker can easily inject SQL without using quotes, as you see here, and this will be the resulting query that will be sent to the database server. Of course, this complicates the SQL injection attack a bit since the injection payload must contain no quotes, but there are ways to work around that. For example, here is one technique for injecting string values without using the quote character. We can encode a string in hexadecimal encoding, and when we run the query, the name column will be compared against the string ABC because this hex value corresponds to the string ABC. This way, we can bypass the need to use quotes in the injected payload. So make sure that numeric parameter values are also enclosed in quotes to prevent SQL injection. Another important note is that special handling must be done for the SQL LIKE operator. The LIKE operator is used to search for a specific pattern in a column. Consider the following SQL query. Select everything from products where name like name plus %sign. What this does is search for all products whose name starts with the value of the name variable. So for the LIKE operator, there are two additional SQL special characters that we need to escape. %sign, which matches an arbitrary number of characters, and underscore that matches any single character. We must escape these characters in the user input to remove their special meaning. If we don't do this, it won't lead to SQL injection in the traditional sense, but it will allow the attacker to manipulate the search condition a bit. For instance, if an attacker includes a % at the beginning of the input, this will allow the attacker search not only names that start, but also that end with this value. The attacker could also use these characters to construct a complex search pattern that might result in a denial of service condition for the database server. Therefore, it is better to escape these characters unless we intentionally want to give users such a powerful search capability. Alright, that's it about escaping. Another SQL injection prevention method is to use parameterized queries. Here is how it looks in PHP. First, we call the prepare method passing our SQL statement. However, note that instead of specifying values here directly, we use placeholders which are denoted by a question mark. Next, we use the bind param method to bind variable names that hold the respective data values. Here we can specify the format for values, S for strings and I for integers. Once we call the execute method, the data contained in these variables will be read and sent to the SQL server. Now, the benefit of parameterized queries is that it automatically escapes untrusted data. In fact, in most cases, the data is not even escaped as it is delivered to the server in a different type of data packet. So this makes it a conceptually different way of sending SQL queries to the server, as here we are sending the SQL statement and the data separately. So this method separates SQL statements from data, which also makes our code more readable. This way, it is very easy to check the code and ensure that SQL statements are hard-coded rather than being constructed dynamically. For these reasons, parameterized queries are the preferred method of preventing SQL injection. Unfortunately, similarly to escaping, parameterized queries are not able to handle all corner cases. For instance, special characters of the like operator must still be handled manually. We can use a placeholder for the like operator, but it does nothing to escape the special characters of the like operator. Therefore, we have to remove them from the input data manually and then add them back where we want them to be. It is important to note that here we remove these characters rather than try to escape them. This is because to safely escape these characters, we would also have to escape the / character. But this would complicate the code, so it might be easier and safer to use the escaping approach that we covered on the previous slide. Also note that here we are modifying the value of the name variable after it has been bound using the bind param method. We can do this because the bind param method binds the variable by reference, not by its value. The value is read at the time of execution, not when we bind it. This allows us to reuse the prepared statement, executing the same statement with different values without having to prepare it again. This approach works well in loops, and such prepared statements can provide a significant performance benefit. And finally, we cannot use parameterized queries or string escaping to sanitize identifiers such as table or column names. In such cases, validation against a whitelist of allowed values must be used. Limiting database user privileges is an important measure for reducing the impact of an SQL injection attack. Let's take a quick look at MySQL users and privileges. We can create a user account by using the create user statement, here specifying the username and here the password. In MySQL, user accounts are identified not just by a username, but also by the host from which the user can connect to the server. In this case, the user can connect only from localhost, but allowing remote access will be necessary if the database runs on a separate server than the web application. If we omit the @ and host part, then the user will be allowed to connect from any host. To grant the user permissions to a database, we can write grant all privileges on database name, all tables, to the user specified here. And that's it. The user will have full privileges to the database, and we won't have to deal with database permissions ever again. This is how the vast majority of database access is configured in practice. However, the problem is that this is a bad practice from a security perspective, as it does not follow the principle of least privilege, which states that components of a system should only have the permissions they absolutely need to perform their function. Here, we should segregate users and limit their database privileges. The principle is that the application should use the minimum database permissions it needs and should connect to the database with different credentials for each trust distinction. For example, if the application performs only reading of data, then only the select permission should be granted, and only on the tables that the read-only user must access. In this case, an authenticated user may read products from the products table, but there is no reason why it should be able to read data from the orders or customers tables, for example. When an authenticated user is accessing the website, the application should use another database user that can select, insert, and update records in the orders table. We can apply even more granular permissions on specific table columns. For example, here we allow the user to select the ID, name, and email columns from the customers table. And here the user is allowed to update only the email column in the customers table. Similarly, when admin users connect to the admin panel, the application should use a different, more privileged database user, but admin privileges must also be limited. For instance, the admin user may need to have read-only access to the logs table, but there is no reason to grant delete or update privileges for the logs table, and so on. Now, setting this up is a lot of work, as it requires carefully auditing every user type and resource to determine what operations, if any, the user must be able to perform on the specific database resource. But if done correctly, the exploitation of an SQL injection attack would be severely limited. Finally, the application should never connect to the database as the root user or any other user that has been granted database admin privileges. This is because database admin privileges can be abused to execute attacks that go beyond exploiting the data stored in the database. The database root user can access the database user account passwords. In MySQL, information about user accounts is stored in the MySQL user table. Passwords are stored hashed by applying the SHA-1 function to the password twice. As you can see, there is no salt involved, meaning that these hashes are susceptible to rainbow table and multi-user cracking attacks. For cracking such password hashes, the hashcat tool can be used, passing -m300 to specify that this is a double SHA-1 hash, specifying the list of hashes to crack, and a list of passwords to check against. This rocku.txt file comes from the Kali Linux word list package and contains over 14 million passwords from a data breach of the Rocku website in 2009. To speed up cracking process, Hashcat can use GPU if a supported graphics card is available on the computer. Anyhow, it takes less than a second to find the corresponding plaintext password for this hash value. Usually, if an attacker has access to the MySQL user table, the attacker can likely read any data from the database anyway. However, cracking the password may still be useful, as it might be reused for other services. Note that the password hash of the current user can be obtained by executing the show create user statement. The problem, however, is that these type of show statements cannot be used inside a select statement. So it may be problematic for an attacker to obtain this information through an SQL injection attack. Now, if password hashes cannot be dumped, online password guessing is also an option. Here, one would connect to the database server, trying various passwords until the correct one is guessed and the connection succeeds. Here, the Hydra tool can be used to automate such attacks. As you can see, such online password guessing is much slower, as in this case, it is able to push a little bit under 8,000 tries per minute. But still, this type of password was found in less than a minute. So the moral here is that strong passwords must be used, especially if the database server accepts connections from remote hosts. Then the database root user may gain the local file access capability, meaning that SQL statements could be used to read and write to files on the database server. This, however, requires the file privilege, which by default is granted only to the root user. So when we use the statement grant all privileges, such special privileges are not granted. To grant these permissions to regular users, the privilege must be specified explicitly in the grant statement. Anyhow, to read files, the load file function can be used. Here, however, it can only read world readable files. This means that it is not enough for the file to be readable by the MySQL system user. It must be readable by all operating system users. To write files, the into out file clause can be used. This allows exporting the contents of a table into a file, and if necessary, column and row terminators can also be specified. Assuming that the database server and web server run on the same machine, an attacker could abuse this to write a malicious PHP file under the web root directory. Then, load file can also be combined with into dump file to copy files to the web root. A dump file works the same as out file, but it writes data without applying any formatting. An important restriction is that the target directory must be writable by the MySQL system user, and for security reasons, this does not overwrite existing files, which means that the destination file must not exist. Here, MySQL provides a system configuration variable secure file prev, which can be used to limit the location in which files can be read and written. We can see the configured value by using the show variable statement. By default, it is set to an empty value, meaning that no directory restrictions are enforced. Therefore, it is a good idea to set this variable to a specific directory when hardening the configuration of a MySQL server. In certain cases, the database root user may also gain the capability to execute system commands on the database server. The idea here is to exploit a user-defined function. User-defined functions allow users to extend MySQL functionality by creating custom functions. These functions can be written in C or C++ and must be dynamically compiled as shared libraries. An attacker would need to write a malicious UDEF library into the MySQL plugin directory, which is configured by the plugin configuration variable. Here is how it could look. Here, the attacker downloads Raptor UDEF, which is a simple function that can be used to execute system commands. The attacker then compiles the function and copies the resulting shared library into the plugin directory. Next, the attacker must load and execute the malicious user-defined function. First, the function must be created using the create function statement. This statement can only be executed by the database root user, as it requires the insert privilege on the MySQL database. Once the function is created, any user can call the newly defined doSystem function, which will execute any command it receives using the system user under which the MySQL database process runs. In this example, the system command ID is called, redirecting its output to a file. Then, using the load file function, we can read the content of that file, which shows that the MySQL database process is running under the MySQL system user. So at this point, arbitrary system commands can be executed as the MySQL user. Typically, an attacker would execute a reverse shell to gain remote control over the compromised system by making it connect back to the attacker's machine. Now, the biggest obstacle to this attack is that this plugin directory is normally writable only by the system root user. This makes it difficult for an attacker to place there the malicious library. This, however, becomes feasible if the MySQL process is running under the operating system root user, which is an extremely dangerous configuration. In such a case, the attacker could use the select into dump file clause to write the malicious function into the plugin directory. And this would allow the attacker to execute arbitrary system commands as the root user, effectively completely compromising the entire system. But okay, on that note, we will end the lecture. Good luck with the homework.